Hi everyone, my name is Leo, and today we're going to talk about WindVision, or how an attacker could chain a series of bugs to take over your TV account. This talk is split in 4 rough sections. We'll start with a few introductions, then we'll take a deep dive into the vulnerabilities, then we'll go over the disclosure process, and finally we'll close with a few tips for both developers and security researchers. A few words about myself. My name is Leonidas Tsaousis, and I'm from Greece, where this talk is currently recorded from. This research was conducted while working for F-Secure, previously known as MWR Info Security. I have a bit over 5 years of experience in the industry, earning a couple of certifications along the way. For the most of this time, I've been a mobile security enthusiast, but lately turned into Active Directory and Red Team stuff. And although I've given this talk in one more conference this year, I'm very, very excited to present at ROOTCON, but also pretty sad that I can't visit the Philippines, surely next year. Wintelas, or just Wind, is the second largest telecommunication provider in Greece, recently acquired by United Group. And WindVision is a digital television service allowing for live and on-demand streaming of sports, Greek TV channels, movies, series, and so on. It comes with a dedicated set-top box running Android TV, or you can just download the mobile application available for Android and iOS devices, log in, and watch TV on the go from your smartphone. It's also worth introducing Zapware. Zapware is an IPTV infrastructure vendor. The solutions are used by telecommunication providers of multiple countries around the world. Some of them are A1, with presence in Croatia, Bulgaria, Slovenia, and Austria, Orange from Belgium, and Amplia from the Caribbean. The findings we'll talk about actually affect Zapware's solution called Nex4, which is what WindVision is using behind the scenes, as was observed during the research. Right, so let's jump into the technical analysis. I'll try not to focus a lot on the details, as it's all out there to read through at your own pace. Okay, so before going forward, it's worth taking a glimpse of the future to see how it all looks like from a high level, before we get deep into the tech talk. So here's what the final attack chain looks like. Don't worry if it's too complicated for now. The gist of it is that a malicious application could exploit certain vulnerabilities in the WindVision application and chain them to steal the user's session in what is known as an account takeover attack. But let's get back to the beginning. Let's see where it all started from and how we got to that. So this is literally the first screen you see when you launch the Android application. It all starts from this transition, as in order to log in, you navigate it from the app to a web view powered by Chrome, as can be seen in the URL bar, then back into the native app. This last step is tricky though, as you need to declare a URL scheme and call it to pass any tokens retrieved in the browser back to the app. This is called linking. It's a typical form of Android inter-process communication, or IPC, and it's implemented using an intent filter specifying a data element. An example URL, which the app can then handle, is the following, which carries the code parameter value, as we can see. However, this is not the most secure way to do this, as this deep linking method, evident from the bare intent filter, which does not perform any further verification, presents a problem, and has thus been replaced with a slightly different scheme termed uplinks. Why are uplinks better than deep links, you might ask? When multiple apps declare the same URL scheme, such as https://www.youtube.com, through deep links, the user will be prompted with a dialog box to select the handler application. A wrong click there could lead to the wrong app receiving sensitive data that was intended for the legitimate application. This is known as URL hijacking, and a malicious application could not only declare arbitrary schemes to hijack sensitive URLs, but also trick users into setting it as the preferred handler application, disabling all future prompts. The solution, the developer could instead use an uplink by specifying an additional element in the intent filter, this auto-verify equals true element, that will tell the system, hey, these are my URLs, and I can prove it by hosting an asset link JSON file on that domain, which then skips the handler altogether and opens the intended app, no questions asked. And this is what this JSON file would look like. Essentially, it's just a list of applications that can register this URL. And this file is checked by the system at install time, or when the app is first installed, and not during every URL call. Okay, so that's indeed an issue, but only a misconfiguration so far. As we'll see, this is a pivotal one, though, for the overall attack, as it will allow us to cross the application boundary. For now, we can only just make a note and move on with the checklist. The next question to ask is, where did that code come from? To answer that, we need to dig deeper into the authentication flow. And to do that, we just follow standard methodology. That means we routed the device using Magisk, proxy traffic using Burp, unpinned the TLS certificate using FIDA. And then we looked at the last HTTP request capture after the authentication. So one trick I typically use to figure out what credentials an application needs is to start from the end, look at an actual authenticated API request, progressively strip parameters and headers, repeating it to the server until it starts complaining to figure out the absolute minimum requirements, and then look back at the HTTP history, trying to see where each of these required values were obtained and how. In our case, all that was needed is these two headers, the credential or key passed in the authorization header, and the device ID. Let's start with this authorization key and look at the overall authentication flow. As we said before, when the app starts, it spawns a web view, which immediately reaches the /authorize endpoint of an identity provider server and gets a redirect to the login page. The user is then prompted for their WindVision credentials, a username and a password, which the web view posts to the login form and gets another redirect back to a URL which the app has registered for, allowing for this code parameter to be passed back to the native code. Now back in the app, the code is exchanged for a token, which the IDP sends back in this third step. To make one final step in the authentication process, this time exchanging the token to an AWS server for a key, which is then attached to all API requests through the authorization header, indicating an authenticated session. So here's such an example API request after all this hassle. The key, along with the device ID header, which is probably a hardware identifier, from what it looks like, is sent to Wind's GraphQL API server to fetch user data, such as favorite channels, etc. So this is it. This is what the normal authentication flow would look like end-to-end. But if you remember, in the third step, where the code is passed between the app and the web view, we found that the URL hijack is possible, in which a malicious application could steal this code from the WindVision app and exchange it for a rogue token and then a rogue session key, which can be used to reach the GraphQL APIs and get all user data. Why is that even possible? Is it a vulnerability in the authentication protocol? And what is this protocol we've just seen anyway? After doing some research, this turned out to be an OpenID Connect flow, in short OIDC, with an authorization code grant. So OIDC is related to OAuth 2, and it has had its fair share of troubles in the past. As Mozilla explains, OIDC abuses OAuth 2 to perform authentication, as OAuth 2 in itself is an authorization protocol. While this is not necessarily a problem, if used in the wrong circumstances, it can lead to vulnerabilities. And this is a very common mistake, with such vulnerabilities reported all the way back to 2012. This is why a security extension to the protocol was eventually standardized, called PKCE, or PKCE, to mitigate the threat of authorization code interception. And this is a threat prevalent to mobile apps, such as WindVision, where the authenticity of the initiating client cannot be guaranteed. To do so, PKCE describes the creation of two additional parameters, a state and a verification code, which works as a CSRF token of sorts. It's initially sent to the IDP server as part of the authorization request, and then resent at a later stage when requesting a token. And this essentially allows the IDP to check if both requests came from the same client and that no codes have been intercepted. So back to our case. Since there's no PKCE implemented, a bad app can hijack a code, exchange it for a rogue token, and even get a rogue key. Can we use that key to appear authenticated to the API server, thus achieving a full takeover? The answer is no, as we still have this device ID header which the server needs, so we're stuck. There's still a missing piece. To find out what this is, we once again went back into traffic analysis and eventually figured out that the GraphQL server only accepted requests with a valid device ID header. That is one that has been previously generated and uploaded after the registration process. So we, as a malicious application, can therefore either create and register our own new device ID using our session key, simulating the registration of a new device, which could unfortunately replace an existing device, as Wind only allows up to 4 smartphones to be registered for streaming, something the user would probably notice. Or we could just guess an existing, previously registered device ID and use that in our rogue requests. So after decompiling the application and examining the relevant code, this is how the responsible function looked like. And this is how it actually looks like in a form that makes a bit more sense. We can see that it all boils down to a media DRM instantiation, which only accepts a constant UUID value. And then the getPropertyArray method of this object is called, which is also passed a constant value. So as we can see, there's no uniqueness, there's no randomness involved. This is a function we can copy into our bad application, execute on the same device as the WindVision app, and always get the same value, which means we can essentially regenerate the device ID for the victim's device on demand. Okay, it now looks like we've got all the bugs we need, so let's take a step back and see how we can put it all together. First, we'll hijack the URL and steal the authorization code. Then we'll abuse the insecure OAuth2 flow chosen to get a rogue API token. We'll reproduce this device ID for our victim device to attach in all subsequent API requests. And finally, just demonstrate our account takeover chain with a scary toss notification showing some personal data or whatever, which means we now need such an example API request for demonstration purposes, one that fetches something small, not too sensitive, but still personal to make a good POC. This means we're back into burp. So while looking in my burp log for a juicy API request to perform for demonstration purposes, I bumped into this one. This was literally the first one after authenticating. Can you see anything funny? So at this point, I was wondering what this master pin code was. But if you remember from a previous slide, WindVision has this maximum number of devices restriction, and the user should be able to change this for active ones from somewhere within the app, right? This was indeed the case. The user can manage the devices from the application settings, choosing devices/accounts, type there this master pin codes, and then go to device management, where you could remove, rename, etc. the active devices. So while not necessary for the account takeover chain, as I ended up using the names of the registered devices for demonstration, this handling of the master pin code is bad practice and doesn't really offer any sort of security to the solution. In any case, time to write this bad boy. This is what the project looked like of the malicious application that we coded. On the left, we can see the URL hijacking vulnerability using the intent filter to declare the same URL scheme as WindVision and steal the code. In the bottom right segment, we can see the functions that executed the API requests needed to go from a code to a token and the actual function that reproduces the device ID. And in the top right, we can see some covertness, essentially to call the real app in case anything goes wrong, which is how real malware would behave, hiding any malicious activity from the user. This code for the proof of concept malicious application can be found online on F-Secure's GitHub repositories to play around with. The app, however, is now patched, and there's an update enforcement mechanism in place that will stop you from using an older version to try out the attack, but you might be able to bypass that if you know where to look. To show you how it all looks like, I've included a short video here of the end-to-end account takeover attack. Let's play this. So as we'll see, a victim user with the malicious app already installed will launch the WindVision application. Authenticate using their credentials, and then make this tiny mistake in the handler that will be presented. Which will allow the bad application to steal their personal data, like devices and the PIN codes. Okay, so we found the vulnerabilities, demonstrated how they can be exploited, coded an example malware application and all, but how possible actually is all that? As one could argue that this isn't realistic and this needs a specific malicious application installed on their device, which should have survived Play Store's defenses in the first place, and that they would never fall for this wrong choice in the handler if prompted. On to the first question, we should keep in mind that we, as users, are very unlikely to scrutinize all the features of all applications we install. And even if we would, we've even seen reputable apps turn to bad ones, whether intentionally or through a security breach. So there's realistically no way to be 100% sure. As for the second condition, there are hundreds of cases in the news every year of malicious apps spotted and removed from Play Store, despite the security team's efforts and all the robust defenses in place, purely due to the volume of apps being submitted. Play Store was actually recently found to be the main distribution vector for malware. So all in all, relying solely on Play Store wouldn't prevent this attack. But what about our own defenses? As we saw in the video, this is what the POC application looked like on the handler. The attacker has control over the icon, the title, the subtitle, making it very easy to imitate the victim app. If you're wondering which is the correct safe option, we saw before that it's the loud one, surprisingly, but it should now be more obvious why app links were invented, and that is to keep users free of such dilemmas. And actually, just to give you an example of how this performs in real life, every time I would find an issue like this in a client engagement, I would create a similar POC malware application for demonstration and go around the office to try it with colleagues and see which one they would pick. And it turns out 90% of the times they pick the wrong option, and these are experienced security consultants. Right, so let's now look at the disclosure process and what came with it. So I put my white hat on, made a formal report describing all the issues that I found, a full POC video, provided detailed remediation instructions, and sent all that to both Zapware and Wind. And then I waited some more, as is the case with these situations. It eventually took almost 5 months to go from initial contact to a patched application being released. I was mostly interfacing with Zapware, and throughout this correspondence, I eventually found out that the vulnerabilities only affected Wind Vision, and not all Next 4 implementations, as I initially thought. Although, to be completely sure, I had gone through screenshots of the respective IPTP solutions for other telcos to confirm some sort of web view-based login was used, but that was not the case, as they said. I was also curious to see how many of the issues disclosed were actually fixed after all this time. I'm going to leave this as an exercise for the audience to find out. Spoiler, not many. And the release notes of the patched application were also rather low profile. That's a question I was asked a lot. The answer is no. I was not sued by either Wind nor Zapware. They were actually very respectful and professional, so no drama. It's worth mentioning, though, that I was prepared, as everyone should be, when digging into commercial products. I kept a copy of the terms and conditions and of the app before submitting my report. I didn't mention anything about reverse engineering. It didn't mention anything about reverse engineering, and I didn't actually exploit any accounts, so no foul play. But better safe than sorry. Apparently, I also got my 15 seconds of fame, as there was at least one news page that caught wind of it. Fun fact, I only found out this when making the presentation, which leads us to the final section of this talk. So before closing off, I'd like to summarize with a few quick tips for mobile developers among the audience. First, OAuth is hard, and so are all of its variants, which means that implementation bugs will always exist. Just make sure to pick the best method for the occasion and implement the protocol according to standards. Do pay attention to your IPC endpoints. This is where the code crosses the app boundary, and do make use of HTTPS if using a custom URL scheme like WinVision did, so that you could leverage secure app links that keep the user safe and free of confusing prompts. When generating IDs, employ some randomness so that no one can recalculate them. And finally, keep application-level authentication credentials local, if possible, such as PIN codes. Don't send them to the server, don't get them from the server, and use secure APIs like the Android key store to store and check them locally. For researchers watching this, I'd like to encourage you to give it a shot. Do tinker with the apps you use every day. You might find interesting bugs. If you do find something, don't stop there. Cover as much of the attack surface as you can, looking at the whole picture, which could allow you to discover more issues, although seemingly low impact, as it may be possible to combine them and come up with something of greater effect. And finally, I'd like to thank a few people for their contributions. First of all, Oli, who took the unattractive role of reviewing my initial blog post, which was very bad in the beginning. It is, I think, a bit more okay now, thanks to him. Rian, for really helping me go public with the research and just constantly telling people about this afterwards so that I didn't have to. Ken, from F-Secure's US office, he knows why. Jay, for reaching out to invite me to ROOTCON, making this presentation a reality. And last but not least, my father, who provided the actual WinVision account that I use for testing, the IDs and tokens of which you saw on all slides. And by the way, these all still work months after the requests were initially captured, so I had to redact them all. And this is it. hopefully just in time. Thanks for watching and enjoy the rest of the event. Hack the planet.